Good afternoon, everyone. Today we're going to start our discussion of time series. Time series is a very important topic, especially in the field of economics, in finance, and also in other sciences, even marketing and operations. Now, time series deal with a type of data, as we learned before, that's sequential in nature. We learned before the differences between cross-sectional data, time series data, and panel data. We learned how to model a cross-sectional data. We learned how to deal with panel data. Now we're going to learn how to model time series data. Okay? So with time series, what's the purpose of time series? Many purposes for time series. You're able to forecast. We're able to forecast future values based on past data. Okay. We're also able to identify trends, seasonality, and cycles. And for some, they would like to understand more the behavior of the data. So they're interested in understanding the underlying process behind the data and also anomaly detection. A time series may have several components. It may have what we call trend. It may have seasonality, and it may have cyclicality and an irregular or random noise. Okay. Trend is self-explanatory. It means the data is going up or going down. Okay. Seasonality means there are some patterns that you can see going up. You have peaks and troughs. Okay. Peaks and troughs on a regular basis. Cyclicality is more difficult to detect because it requires longer periods of time, and it's not regular. Okay, it's not a regular thing. It's a long-term fluctuation. Okay, and the period, it's not like seasonality where you have, let's say, in the month of February, sales go up because maybe the company is in the flowers industry or chocolate industry. So if they take a look at their past data, they see some movement as far as sales is concerned, a going up movement in February or in December or in other months. Okay, so that's what we mean by seasonality as compared to cyclicality, where you can't really detect. It's difficult to detect it. There are, of course, some tools that can be used to at least have uh, a a slight detection of cyclicality. So our focus in this subject will be more of the trend and seasonality. We're not going to do with the cyclicality. Okay, so we're going to make use of here. Christian asked me about this. Kindly change this class. We're going to use air passengers for our data. So air passengers. Oh, by the way, first let's load first this packages forecast, T series, TTR, KFAs, ggplot, and quant mode. Okay, I'll give you a few seconds, class, to use Pacman to load these packages. And when you're done, kindly please chat in the chat box. As usual, class, please interrupt me. Please tell me if I'm going too fast. Okay, good, thank you. So the data that we're using is air passengers. Okay, this is actual data coming from the quant mode package. So data, let me delete all my data here so that we're on the same page.
So, sandali po, wait lang. Go back po kung yun, which ones yung kailangan ni-load.
Sorry.
Can you go back po yung which ones kailangan ni-load sa Pacman?
It's there. Nasa ano. Andito. I think you have it. Ito, di ba? Did I provide it to you, class?
Wala po din sa na-copy ko sa
Wala. Hindi ko na nalagay, class. Paki-chat please kung hindi. Sorry. Hindi ko ba nabigay? Class, feedback please.
Parang wala po siya sa notes, sir.
Wala, sige. Yan. Ano na lang, sorry. Hindi ko yata na-copy. Okay. So kindly copy that, class. Those are the packages that we need to load. Okay, thank you, Christian. Okay, so we're loading air passengers, class. Data air passengers. And where's my air passengers? Why didn't it load? Ayan, okay. Here. It's a, if I click this class, it's a vector. Here. Okay, let me delete this. Click. Let me print air passengers. Okay, here. So it's under the values section of your environment, which means this is a vector. It's not a data frame. It's a numerical vector. So it consists of data in millions of airline passengers from 1949 to 1960, US data to, no? So this is actual data. And let's let's shorten the name of air passengers so so that we don't have much difficulty writing it. Let's call it AP. Okay, Control Enter. So we now have this. We now have AP also. It's same as air passengers. And then let's plot. Let's plot AP. Control Enter. All right. So this is the plot of AP. And what's the what are the qualities? What's the composition of AP? Number one, you can see that AP has trend. Okay, it has trend because it's generally going up, right? So trend is the tendency of the data either to go up or to go down. So this is an upward trend. A downward trend would look like this, of course. Okay. So our data, AP, has upward trend. Not only has it upward trend, you notice that there are, okay, regular peaks. These peaks are those data that are highest. They come at a regular basis and then it goes down. Okay, you have your troughs here. Peaks, P-E-A-K-S, peaks, and troughs, class, troughs, T-R-O-U-G-H-S. Okay, so the data is displaying what we call seasonality. So these are airline passengers. So most probably, if I recall right, summer season sa US, so July to, June, July. Okay, June, July, and then or July, August ba to? September yata to, yung troughs, no? September, these are the low moments, lows and the highs. So this data, not only does it have a trend, it also has seasonality. We can't say anything about the cyclicality. The data is too short. 12 years is too short in order to determine a long-term behavior of the data. Okay, so we look at trend and seasonality. And of course, those that are not part of your trend and seasonality will form part of your irregular or random component. Okay, so let me clear this. All right. Now, in time series analysis, there are some models which we will not be able to reach that model, ARIMA model today, but there are some models that require your data to be stationary. Okay, so this is a data that's not stationary. Why? If your data has a trend, it's going up, and also the variance does not seem to be constant. Okay, what I mean by constant variance is that I'll explain that in a while. Okay, the the variance or the standard deviations of your data does not seem to be does seem to differ over time. So in this case, there's a trend. Since there's a trend, therefore this is not stationary. Also, we may say that the uh, the data seem to have non-constant variance. So let me explain what non-constant variance is. So if you have a data that behaves this way, their class, so there seems to be a fanning. Imagine it's a fan, F-A-N. No? So you know a fan, when you open it, then you can see there the funnel effect. Okay, seems to be increasing over time. This one, class. At this specific period, the variance seems to be equal to this one. But at this specific period, the variance is at this level here. So across time, you can see that the variance is increasing. So therefore, it's not constant. So if the variation is not constant, then it's not stationary. If there's a trend, then it's not stationary. Okay? So how do we treat this? There are certain models in time series which requires stationarity. It requires that your data should not have a trend. It should not be going up like this. So how should it look like? If your data does not have a trend, then it should only look like this one. Okay, this is a data that has no trend. Okay, this is well might as well be the average. Okay, so you can see that its mean is constant mean. Anywhere you look at your data, if I look at this period, the average is this one. If I look at this period, the average is this one. Okay, that's constant mean. Okay, so if your data has constant mean, then it's stationary. Also, if your data has constant variance, so let me, okay, you can see here that aside from the fact that it has constant mean, the variance is also not fanning out. It's not increasing over time, neither is it decreasing over time. So in this case, we say that your variance is constant. Okay, so if there's no trend, which means the mean is constant, the average is constant, and the variance sigma squared is equal to constant. Therefore, we have a data set that's called stationary. So why is it important for a data to be stationary? Because there are some models, let's say, just like ARIMA model, where your data has to be stationary in order for us to use that. Now, why is it important to study ARIMA? Because ARIMA is one of the most powerful methods in modeling time series. So we'll discuss that most probably next meeting. Okay, so now what if your data is not stationary? Then we will have to do transformations. We will have to tweak the data so that it becomes stationary. Okay, but before I discuss stationarity, how to transform your data, it's not enough that we just look at the data and manually or visually say that this is not stationary, although it's obvious from here. But there are some statistical tests to help us. One of the most important statistical tests is ADF. This is your augmented Dickey-Fuller test for stationarity. However, let me tell you that there is a weakness to this method, the ADF test, okay? Okay, the null hypothesis here is that the time series is not stationary, okay? And we believe so, that the time series is not stationary because there's a trend. So we should be expecting that the p-value should be greater than 0.05 so that we will not reject that null hypothesis that the time series is not stationary. So if I run this, you'll notice that the p-value is 0.01. Okay, which means that we reject the null hypothesis that the time series is not stationary. So the alternative is that it's stationary. Okay, so we have a problem here because the time series is not stationary. So we were expecting a p-value that's greater than 0.05. So ADF, the augmented Dickey-Fuller test, has its inherent weakness. Okay, especially when the data has a strong trend. In many instances, it's not able to capture that trend. Okay, so good thing, there is another test. There are other tests, and another popular one is KPSS test. But KPSS test sometimes also has its problems, but it's more of the ADF test. So it's Kwiatkowski, Phillips-Smith-Shin test. So that's the KPSS test. Okay, so I explained here why this is better than the ADF test. Although there are some instances where, okay, where the KPSS test also fails. Okay, so the opposite KPSS test has an opposite null hypothesis. So for ADF, the null hypothesis is that there is a unit root, which means that the data is not stationary. For KPSS test, the data is stationary. So that's the difference between them. All right. So if I, so the data is stationary. Okay. So which means no trend. All right. So let's run this. We use KPSS.test for AP. Okay, and null is equal to trend. Again, the null hypothesis here is that the data is stationary. Okay? And therefore, pag stationary siya, no trend. Okay, let's run this KPSS test. And you see that the p-value is 0.1. Okay? And, oh, sorry. Wait, mali yata yung null hypothesis ko. Time series is stationary. It tests whether a series is stationary around the trend. Is it stationary around the trend? Okay. Hindi. May something, ano kasi, yung null hypothesis ng KPSS test, medyo ano siya, medyo tricky, ano? Let me just quickly review this. Which means it tests whether a time series is stationary around the trend. If it's stationary around the trend, then, okay, p-value is 0.1, therefore, it has a trend, therefore, it's, sorry, unit root not stationary. Okay, ito, stationary siya. Okay. Alright. Kasi magkaiba yung ano null hypothesis ni ADF. Ala, medyo parang na-confuse ako dito. Sorry class. Sa KPSS test, ang null hypothesis is that the data is not stationary. Okay? So dito mali tayo kasi here we are 0.01, so we reject the null hypothesis that the data is not stationary. No? And we're saying that it is stationary, which is wrong. On the other hand, for the KPSS test, we're saying that the data is stationary. Okay? And the p-value is 0.1. Okay? All right. Really class, huh? Oh, something's wrong, class. Kasi ito, ang null hypothesis natin, stationary siya. So it tells us that we fail to reject the null hypothesis that it is stationary. Okay. I'm sorry about this, no? Bakit naging ganito tong KPSS test? Let me backtrack a bit here. Okay, I'm sorry about this. I'll leave this first. I'll leave the test for stationarity using ADF and KPSS test. Okay, I'll leave this first. And anyway, we will be using this when we go to ARIMA. Okay, so let's just go back to this when we go to ARIMA. Let's first deal with the different methods. And the first method that we're going to analyze is the smoothing methods. Okay, so one of the most, the easiest, one of the most common method in, by the way, sorry, forgot this, okay. So we can make use of the STL function where we can decompose our data. When you say decompose, we convert it into its seasonal components, its trend components, and its irregular components. Okay, here, Control Enter. So this is decomposed air. It's a list of 8. Let's plot this. We can see now. Let me plot this. There. Here, class. So you can see here this is our data. This is our seasonal component. This is our trend, and this is our irregular or random component. Okay, so you can see here that the AP has seasonality and it has trend. So definitely this is not stationary. So when your KPSS or your ADF test tells us that this is stationary, then we have a problem. Okay, let me check those statistical tests. Okay, so what are the methods that we're going to learn about time series? The first one is simple moving average. It's one of the easiest, one of the most common, and it's particularly useful for forecasting. Okay, now SMA, simple moving average, smooths out the fluctuations in a time series. So our time series, just like the AP, okay, let me plot. Okay, where's that? Here na lang. Let's plot AP. Okay, here. So this is our airline passengers. So what happens when we use SMA class is that it will tend to smooth out your data. So what do we mean by smoothing out your data? When you say smooth your data, it will remove all these seasonalities. Try to remove those seasonalities. Okay, depending on the lag. So this is one of the possible things that will happen when we model our air passengers using SMA. So is this a kind of a weakness? Yes, it is. It is kind of a weakness because it's not able to identify the peaks and troughs of your data. It may be able to get the trend, but not necessarily the seasonality. So that's a weakness of the data. Okay, so let's distinguish between, okay, so we have the moving average. So the idea is to average data over a fixed window of time. So for example, let's get the average of the 12 months. Okay, so you get the first 12, get the average. So that will be your first SMA value. Then go to the next 12. Okay, so that will be, example, from data 1 to data 12, that's your first 12, right? You get the average of that. That will be the first value of your SMA model. And then you go from data 2 to data 13. So you keep on moving. You could keep on moving, getting 12 observations. Okay, I hope you can visualize that. So imagine you have data 1 up to data 100, for example. So if you're using SMA 12, you'll get the first 12 values and then get the average of that. So that will be your first value for your SMA 12. And then you, from 1 to 12, then you move from 2 to 13. You get the average of that. And then you go to 3 to 14, get the average, and then 4 to 15, etc. So you keep on moving down, moving down the line until you reach the maybe 89 to 100. Okay, so that will be now your last value, because you can continue to uh, data 101 because there's no 101, assuming you only have 100 observations. All right. Okay, so the lag matters. The window size refers to lag. So you can use SMA 7, SMA 14, SMA 30. So what does SMA 7 mean? You get the first 7 observations, average that. That will be your first value for SMA 7. And then you go to 2 to 8, 3 to 9, etc. Okay, is that clear, class? Is the concept of moving average clear? Feedback, please, class. Okay, good. Good. So you're just moving. You're just moving one period at a time. It's not 1 to 7 and then 8 to 14. It's not like that. It's 1 to 7 first. If it's SMA 7, 1 to 7, and then 2 to 8. That will mean another average, another value, and then 3 to 9, etc., etc., etc. Okay? So that's your smoothing average. So the formula, class, is this one. Okay. All right, so I'll share this. I forgot to include the, share this in the chat box, Control V. Okay, and just remove the old one, class, because for the old one, I failed to put this inside. Okay, I did not put it inside this one also. Okay, so let's remove that. Okay, so this is the simple formula for a simple moving average. Okay, you have to define your K. Is K 12? Is K 14? K refers to the number of the number of periods that you're going to, the number of lags that you're going to average. So my example a while ago was 7 or 12 or 14. Okay, where the SMA is your moving average at time t. K is the window or the lag. Okay, why are your actual data points? Okay, so it's best to take a look at this. Now the question is which lag to use. Okay, well, it depends on the data that you're looking at. For some data, they may require a shorter lags. if it's monthly data, maybe you can choose 12. If it's weekly data, you can choose 7. 4 to make it 1 month. And usually it's trial and error. Okay, and there are different methods in order to determine what should be the lag. But that's not our concern now. So what did I use here? I think 12 here. Okay, no. So let me share this with you. And what I did here was we did it in I included this in the other class. I put additional lags because my original example I think was only 12. So let's compare what will happen if you have a lower lag, let's say 4, and the function is SMA, our object is AP, and then n is equal to 4. Then let's plot it. Then here, maybe to distinguish it, I'll choose here blue, and then green, and then what else? I don't know, maybe violet. Okay, let's just see, class. Okay, all right. So here we're creating 4 SMAs, simple moving average. One is lag 4, one is lag 12, one is lag 24, one is lag 36. So I hope you know, I hope you understood what I mean by lag 4. Lag 4 means you're going to get the first 4 values and then get the average. So the SMA4, of course, will have a longer time series, a longer plot, a longer data than SMA12 because SMA12 will start at, will get the average from the first 12 observations. Of course, SMA36 will have the least of this. Okay, so let's run this and plot them, class. Okay, let me rerun this. All right, so here I have 4 plots because I have SMA4. Let me start with SMA36. So this is SMA36 class. Notice that it starts on 36, month 36. Our data is monthly data. Okay, so it got the first 36 observations, got the average of it, and that will be your first value. Okay, and notice how it behaves. Okay, so the longer the lag, the more smooth your data will be. In fact, it's just like, it's practically almost just a bit of a curve, but it's practically a straight line. Okay. Now, how about 24? So 24 is a little bit less linear than compared to 36, and so is S12. And notice how this began on month 12. Okay, so it has more, say, it's less linear compared to 36. But take a look at number 4. See how SMA4 almost mimics your data. And why is that so, class? Because if you have a shorter lag, then you're not really able to smooth out your data, hence this behavior. Okay, so remember that, class? The shorter the lag for simple moving average, the more it will be less smooth. SMA 36 is a very smooth class. Okay, so let's go here. All right, so here I just created, okay, a function. Okay, so I defined the lag values 4, 12, 24, and 36. Okay, I placed here plot. Okay, for lag in lag values, here 4, 12, 24, 36, it will be placed here. It will use the filter function. This is your object AP, and it will repeat 1 over the lag. Okay, how many times? Okay, what will it repeat? 1 over the lag. Okay, sides is equal to 2. So you don't have to really understand now what's happening here. But let's just take a look at the answer here. Okay, so in one plot, you can find here the differences between your there. So this one is your SMA4 because it started after 4 periods. This is your 12. Okay, this is your 24. And where's your 36? 36 is somewhere here. I think it's here. Okay, and you can see that the most, we can't really see that much, but the most smooth here is your SMA 36. And the least smooth, this one that seems to follow the trend, is your SMA 4. Okay, SMA 4. In fact, class, what will happen if it's just 2? Okay, of course, it cannot be 1 because you cannot get the average of 1. 1 will be just the time series itself. So if you're just getting the first 2 values, and maybe just let's plot it here, class. Maybe for purposes of just discussion, Control C, I'll just run it here. Just to separate it, class. SMA2, so N is equal to 2. 2 lags. Okay? And lines SMA2, AP. All right. So let's see. All right, see, class? So you can see how it clearly mimics, because you're just getting the average of the value yesterday and today. Okay, just get the average of that. Okay, and this tells us that the data is really correlated. The data yesterday is correlated to the data today. So this is SMA2 class, no? So I hope this proves that the lower the lag, okay, the more truthful it is to your data. The higher the lag class, the more smoothen the data is. Okay, so you have here some interpretation. SMA with lag 12, it will smooth out fluctuations at a monthly level. Okay. SMA at 4, because the data is monthly, so that's 4 months. That's hindi nga quarterly, no? So pag 3 ang ginamit natin, 3 months, that means quarterly siya, no? So magiging quarterly yun. So 4 is 4 months. All right. Okay, clear so far, class? May I request your feedback so far, if clear yung simple moving average. Okay, good. Thank you. How about the others, please? Okay. All right. Now, let's check, let's compare SMA 4, SMA 12, SMA 24, and SMA 36. How do you compare the performance of our model? If you take a look at this, so this is the blue one is the original data. Let me annotate. Here. Okay, the dark one, the dark one is our original data. Okay, and this one, of course, this one class, this is the violet one, is your SMA4, right? It started here. Now we can compute for the residuals. So for example, this is your actual data point here, this one. And if you compare that to your SMA4, this one, okay, this is the prediction of SMA4. The difference between your actual value and your predicted value, as you know, that's your residual, that's your error. Okay, so of course you'll see that the residuals of here, for example, this one, this green one, the residuals of the models that have a longer lag is higher. Okay, it will be higher. So what we can do is to compute for all of the residuals. Okay, but we don't sum them up. Remember from your regression, if we sum up the residuals, then this will give you 0. So what we do is to square the residuals. We square them and then get the average. Get the average, your n. So this will give us the average, and then get the square root. So this one, this is a special name. This is called your root mean square error. That's your Ramsey class. That's your Ramsey. And what's this class? Squared residuals. Then you get the mean, and then you get the root, square root, Ramsey. So Ramsey is one of the most popular ones in determining which is a better model. So of course, the lower the Ramsey, the better the model is. And just from the look of it, class, I know you'll agree with me that the SMA4 is the better model because it does not really smoothen out the prediction. Okay, so if we go here, class, let's take a look simply at this function. So we're creating this Ramsey function. Okay, and then it's a function where you have to input actual and the predicted value. Okay, so we're creating this valid index, and is NA do not include the NAs. Why will there be NAs? Because you have different periods. Okay, for example, for SMA4, you'll have a comparison at period number 4, at month number 4. But for SMA12, you will not have any comparison with period number 4 because SMA12 is not yet existing at period number 4. Okay, so from period number 4 up to period number 11, SMA will be missing value. Same thing with SMA 36, all the more, because SMA 36 will not have values from 1 up to 35. It will have its first value on period 36. Okay, so you cannot compare the actual value, the air passengers, with SMA 36 from data 1 up to data 35. You can only have a comparison at month 36. All right, so for SMA 4, you have starting with month 4 up to the end. From SMA 12, from month 12 up to the end. For SMA 24, from month 24 up to the end. 36, you know. All right, so you'll have differences in terms of the computation of Ramsey. Okay, but let's take a look at this. So here, what will happen is that it will generate the EMA, and then it will create the Ramsey result, okay? And then it will print it. Okay, so let's run this. And the lags are 4, okay, let's include 16. Oh, sorry, 4, I missed out 12 here. 4, 12, 24, up to 36. Okay, 4, 12, 24, up to 36. Okay, I think the original one was 12, 24, 36 only. So let's run this. Okay, and let's see. All right, so there's a warning here that log 4 is longer. All right, so log 36 is 137. Okay, log 4 is 56, the Ramsey. So these are the measures of the Ramsey: 56, 107, 131, 137. So you notice that SMA 36 has the highest Ramsey, which means that it has the highest root mean square error. Okay, while as expected, log 4 has the lowest. So we can modify this a bit by trimming. Okay, so here we're going to remove. You can see here that I placed here NA.omit. Okay, so we're removing those that have no. Okay, so here 4, 12, 24, 36, and if we run this, wala pa. There. So you notice that it did not generate any more of the error terms. However, I noticed that there was a change in the computation of 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 36. Okay, I'll have to figure out, class, about this function, why there's a discrepancy. Okay. All right, but still, class, we can see that log 4 outperforms in terms of Ramsey. It outperforms the others, the log 12, log 24, and log 36. If that's so, then why choose longer lags? There are reasons. In stock trading, usually we don't choose lower lags, either 12 and what's that? What 50 and 200, yeah. And there's a reason for that, why we choose longer lags, and we'll discuss that in a while. Here, that's the next one. Okay, so here, class, SMA can be applied also to stock trading. So it's not just simply computing for the averages of the past X lags. SMA has its role in stock trading. May I know, class? Chat, please, yes or no, if you discuss in your, I don't know, investment, what's your subject on investments? If you discuss some of these technical trading rules, for example, the simple moving average used in deciding whether to buy or to sell the stock? Yes or no, please? Class? Yes, okay, good. How about the others? Yes or no, please? Mm. No recollection? Hello, class. Waiting for your feedback, please. A yes or no will do, class. I just want to know if you, okay, yes, yes, okay. All right, so you're familiar with this class, no? So an example, a trading rule is that if the 50-day simple moving average crosses, if it goes above the 200-day moving average, it is often interpreted as a buy signal, okay? While a crossover below, so 50-day moving average goes down the 200-day moving average, it will see, it will indicate or signal a sell. Okay, so we're going to use the quant mode package. The quant mode package is a very powerful package in downloading stock prices. So quant mode has this function, get symbols. Just have to identify the ticker symbol. Here I'm using Apple. This is the ticker symbol of Apple. And the source is from Yahoo. Okay, so we're going to get prices from Yahoo. And then the date is from January 1, 2020 up to the date today, systems that date. Okay, so if you run this, then it will generate an object here, okay, called Apple. Let's see, control enter. And you can see that the object Apple was generated and it's here, Apple. Okay, if you click this one, let's view Apple. So it provided us 1,312 observations from January 2. Why January 2? Because January 1 this did not have a trading day. It was not, it was a holiday until today, date 3/21. The latest trading day was last Friday. Okay. All right. So we have this data open, high, low, close, volume, and adjusted. So it gives us uh, complete information that you can see from at least the prices and in the volume. Okay, so what we're going to do now is we're going to create a simple moving average. Okay, so here I'm creating SMA 50. So the function is SMA, simple moving average, and then we're going to get the closing price. Okay, and N is equal to 50. So this is your 50-day SMA moving average for your closing prices. And then how about the SMA 200? Okay, SMA 200. So I run this, control enter. And then if you take a look at the simple moving average 50, let's print this here. You can now see that the first 50 observations are the first 49. This is the 50th. Okay, so this is the 50th. And same thing with 200. can see that there are 200. Okay, this is the 200th row. So this is the average of your first 200 observations. Okay, so let's go back to our code. We will now plot Apple, and then we will include the lines of SMA 50 and the lines of SMA 200. We'll give a legend on the top right. Okay. And then let's run this. Run everything, and you'll have a combined plots of your Apple closing prices, of your SMA here. Okay, so this is the combination class of your SMA. The red one, of course, is your SMA 50 because it starts first. The green one is your SMA 200. So how do traders make use of SMA 50 and 200? Okay, take a look at crossovers here. So when the SMA 50 crosses the SMA 200, then this is a signal, then this is a sell signal. Okay, it's a sell signal. Bababa siya, no? On the other hand, if your SMA 50 here, this is your SMA 50 crossing over this one, crossing over your SMA 200, then that's a buy signal. Okay, on the other hand, this one, okay, your SMA 50 goes down below your SMA 200, then that's a sell signal. Okay, so this is just an example of how SMA may be used in technical trading. There are, of course, other rules aside from SMA. Okay, are we clear on that, class? May I have your comment, class, if you got that? Okay, thank you. All right, so let's now go to EMA. Although we're quite ahead of the class because in the other class, I think I just gave an introduction to this, but we'll do this already. Okay, so what's the difference between simple moving average and exponential moving average? Well, they're both related. Okay, they're both moving averages. The difference is that in SMA, the weights are just the same. So whether it's let's say SMA 12. So if you're computing for the first observation, you average all data 1 up to data 12. When you average it, it means that you're giving them the same weight. Okay, it's 1 over n. Okay, so each of the observations have equal contribution to your to your SMA value. For exponential moving average, okay, it's not. It's a more of a weighted average. Okay, so it gives more weight to the recent observations. Okay, so for example, if you're modeling SMA, let's say SMA 24. Okay, so it's not dividing by 1 over 24. Those closest to 24 will have higher weights. Okay, as compared to, let me give a crude example. Let's say it's SMA 10. For SMA 10, it's 1 over 10 each of the observations, first 10 observations. For EMA, the ones that are close to the 10th, the 9th, the 8th might have bigger weights because they're the ones closest. Okay, those at observation 1, 2, 3, 4, they will have the the smallest. So it's just like a weighted weighted prediction. Okay. All right. Let's take a look at this. Let's. Okay. Could you kindly show the formula? It's in LaTeX. Okay. So this is our formula: alpha times y sub t plus 1 minus alpha times EMA, exponential moving average, t minus 1. So what will happen is that you will predict first EMAT, okay? And then for the second prediction, you will use both the actual value and the predicted EMA t minus 1. Okay, so it's a bit more complicated than the formula for SMA. So EMA is the exponential moving average at time t. Y sub t is the observed value. This is the actual value. EMAT minus 1 is the exponential moving average from the previous previous time. Okay. And then you have what we call a smoothing factor. And then you have the window size. Okay. All right. So let's take a look at this. Kindly change class. Okay. I think this comes first in the file that I gave you. Please transfer this to this code chunk. So let's use first this one where we are defining what EMA function is. So I was editing it and then I erroneously made this as the first. That's why if you try to run this, then it will generate an error term because R will not recognize EMA function. We'll have to define that here first. Okay, hold the line class. Okay, so this one actually we don't need anymore. Okay, but what's important is that we have to make sure that AP is numeric. Okay, because I was running this a while ago, then it generated an error term, so I had to put here to convert AP as numeric just to make sure. All right, so here we're writing this function. We're defining alpha, and then EMA, and then where the EMA will start first. Okay, so you don't have to really know by heart what's happening here, but it is just a function that will compute for EMA. And then we will use this function, class. We will use this function. For example, here I'm using AMA 12. I identified n is equal to 12, and then it will now compute for EMA 12. Okay, so let's run this for us to see how EMA 12 looks like. Okay. Sinama ko na si SMA. Bakit EMA versus SMA? Wait. Okay, but this is the plot class. So this is EMA 12 class. And you can see that to a certain degree, EMA and SMA are quite similar. EMA is quite similar to SMA with small lags. No? Okay, so let's now compare. Let's go down here and we can now run this Okay, we'll compute for EMA 6, EMA 12, and EMA 24. And we're going to use the EMA function that we generated above. It's actually here. Where's our EMA function here? In the functions here. A while ago, we have Ramsey. Here we have EMA function. That's a function to compute for EMA. So we identified EMA 6, 12, and 24. And then let's plot. And what do you see here? Okay. So just like class in SMA, okay, the lower the lag class, the lower the lag, the more your data will mimic, okay? The more your data is not smooth out. Here, EMA 24 class, can see here that although it's not that smooth as SMA 24, but you can see the smoothening out of your data, and it still follows the regular movement of your air passengers data. Okay, so this is a comparison between EMA 6, EMA 12, and EMA 24. All right, let me pause for a while, class. Clear so far? Okay, by the way here, okay, so let's experiment. What if I make this 4? I made it in such a way that when you change 4 here, 4 will be applied here. Okay, so this becomes okay, anyway, I'll not change the name. I'll still call it 12. Let's just see the plot, class. When you have EMA4, so this one, class, diba? EMA4, just like the SMA4 that we used a while ago. Okay, so it follows the it follows the behavior of your air passengers. Okay, or let's see if we use EMA 36. What will be the result? What will be the plot? Okay, so you can see that SMA and EMA pretty much behave similarly. The only difference is that for your SMA, you're averaging. The weight of all your observations, past observations, are constant. Kasi 1/k, di ba? Of average lang siya. While in SMA, may smoothing constant tayo. No? So we give more weights to those that are closest. Okay, kunyari 1 to 12, mas malaki yung weight ng data number 12, 11, 10 as compared to data 1, 2, 3, etc. Okay, let me revert back this one. So you can experiment, class. No? How about we tried SMA 2 a while ago. So will this work here? EMA 2? Two lags. So that's as fresh as you can get because you're only using 2. You're giving a bigger weight to, for example, EMA 2, you're giving a bigger weight to data number 2 because it's the closest as compared to data number 1. So you can see that if you plot that, it really mimics our data. All right. Okay, it's almost time, class. Okay, I wasn't able to, just this one, and then we call it a day. So just like your SMA class, we can make use of EMA in stock trading. So what do we use here? Usually we use 12 and 26. Okay, EMA 12 and EMA 26. So these are the EMAs that's mostly used in signal trading. Okay, so here we are using quant mode again, get symbols. Let's use Tesla from Yahoo, again from 2020 to system date. And we're using this EMA 12 Tesla. Okay, we're using this one, EMA. We're not using EMA function. EMA close, n is equal to 12, and EMA 26, okay, n is equal to 26. And then we plot it, and we see, let's plot this one. And just like, okay, so this is the first one. This is the original. This is your, okay, this is your 26. And this, sorry, this is your 12, and this is your 26. The two, okay? You have the green and the red. And what's the decision rule, class? What's the decision rule? For EMA here, when the short-term EMA crosses above, okay, a long-term EMA, it's a buy signal, just like SMA, class. Similar to SMA. When a short-term EMA goes above the long-term EMA, then buy signal yun. Otherwise, it's sell. So if you take a look at this one, okay, and then I'll end here, class. So there are points when your EMA 12 crosses over here. Okay. Not so clear, no? Okay, there are points here when this point, class, here, for example. Okay, where is that? Those points, for example, this one. Those points when you're shorter, which is the red one, goes below your longer, then it's sell. So this is a sell signal. Okay, this one, so sell, and then here it goes up here at this region. So this is a buy signal. Okay, so this one again is a buy signal. So where your red shorter EMA crosses over beyond the longer EMA, sorry, then it's a buy signal. Otherwise, it's a sell signal. Okay, so let me